Hey everyone, and welcome to the lab on kinetics. This lab is looking at the rate of decoloration of a yellow dye number 6. It's an FD&C food grade dye. And I performed 6 different trials of this experiment. Each trial I did in triplicate. So for trial 1, I didn't have just one container. I had 3 containers. So I repeated this trial 1 basically 3 times. I repeated trial 2 3 times. I just did it all 3 times at once. So the way I set it up is I have little condiment cups, and I put 10 milliliters of water in each one. And then I add the food dye. So for trials 1 through 3, I just put 1 drop of food dye in each. For trials 4 through 6, I put 2 drops of food dye in each. So I doubled the concentration of the dye. I also varied the concentration of the bleach. In trial 1 and trial 4, I only added 1 drop of bleach. In trials 2 and 5, I added 2 drops of bleach. And in trials 3 and 6, I added 3 drops of bleach. So the trial 3 data didn't turn out so great. So you'll see in the protocol here that I have those data points sort of crossed out. So we're just going to use trials 1 and 2, 4 and 5, which is fine because with those 4 trials, we have 2 with different concentrations. We have 2 different concentrations of the dye and 2 different concentrations of bleach to look at and compare. So, trial 1. So I'm going to play the video here. You'll see trial 1, and this is just a guide showing you what trial 1 consisted of. It was 3 containers of 10 milliliters each, 1 drop of food coloring, and 1 drop of bleach in each of these. So I'm going to actually play this and narrate as I go. So this is trial 1. Oops. So I start the timer right as I'm adding the drop. So 1, 1, 1 drop. So it took me about 4 seconds to do that, but we'll call it even. And so now I'm stirring them. I stir them to make sure that the bleach and the dye are evenly mixed. So I just want to keep it moving. Make sure there's good mixing of that solution. And they're starting to fade a little bit. They'll continue to fade. And when I have decided with my eye that they have, in real time, that they faded completely, I point at it. And at that point, that's when you should write down the time. So I have just a fraction of the table here. So you would record, and I can show you what I'm talking about. Oh no. How do I get it to play? Oops. So maybe I can't write at the same time. Boo. Okay, well then I'll just narrate it. So where were we? We were like 30 seconds in. Trial 1. Okay, so keeping an eye out here. They're fading. You can see they're turning like a paler orangish yellowish color. I need some background music. And they're getting even fainter. Now, you'd think they'd all change at the same time. They all have 10 milliliters of water, 1 drop of dye, and 1 drop of bleach. But remember, I didn't exactly standardize this. 1 drop, a drop of the yellow dye might be slightly different in each cup. They might have a slightly different volume. And I used a graduated cylinder to measure those 10 milliliters of water. Also not the most accurate and precise instrument to use. And I used a dropper and dropped 1 drop of bleach. Again, those are not uniform drops. So it is very understandable that we're going to have different times for each of these. So I just called this one at 1 minute and 40 seconds-ish, so that's 80 seconds, right? Nope, 60 plus 40 is 100. 100 seconds for that one. And This one we called it 2 minutes, so that's 120 seconds. And this one 126. So for A, B, and C, for this trial, you would say 100, 120, and 126. And you're going to do this for each one. So now we're going to watch trial 2, and I'm going to stay quiet and let you make your observations. There's 1, there's 2, and there's 3, I called it. Here's trial 3 that I said we're not going to do this one. I graded out on the chart. By the way, this is the chart in your handout that you should be recording each of these on. So we just did trials 1 and 2, and now we're going to watch trials 4 and 5. I made these silent recordings because my husband was playing video games in the background and my cat was doing parkour off the wall. I'll also just comment that another room for error in this experiment is, my eye. So I'm the one who's deciding when the solution is perfectly clear. And of course, my eyes are imperfect instruments as well. So when you're doing the math calculations, you're not going to calculate percent error, but the numbers are definitely not going to come out perfectly because this is not the most precise chemistry, but it's still a good illustration and a good exercise. There goes A. There goes B. And there goes C. And now the last one, trial 5. This one is 2 drops of dye and 2 drops of bleach. that one went. And I called the middle one. And call that first one. In trial 6, we said we're going to ignore this one. So all of your data should be recorded in this table. So for trial 1, the 3 cups in trial 1, the 3 cups in trial 2, the 3 cups in trial 4, and the 3 cups in trial 5. And now you're going to calculate an average for each trial. It's really important in science that when you do an experiment that you run multiple replicates. 3 is actually a really small number. If we were going to do this for better data, we would want to run more trials. We might even do it in something like a 24-well plate where we could do 20 trials or something at once, and maybe have a team of folks who were watching it so that we could get all the times on all of those. Anyway, the more data points you have, the stronger the data. So we only have 3 for each trial, but it's better than 1. So we're going to average each of the trial data, and we're going to use the averages for our calculations. So one of the calculations you're going to do is you're going to actually calculate the concentration of the dye. Now this is also a little bit falsified. So remember, each of those drops of dye and each of the drops of bleach are not exactly the same size. So this was me sort of an average estimate of the size of a drop out of the dropper versus the size of the drop out of the little dropper pipette. So I want you to do, it's sort of a rough calculation because these are not really the actual exact numbers that we're using, but it's going to suffice for this experiment. So I added drops. I added either 1 or 2 drops of dye to each of those cups. The dye, the stock solution was 0.01 molar, and I added it to 10 milliliters of water. And we're going to assume that the drop had a negligible volume. So we'll assume the total volume of our solution was 10 milliliters. And that each drop was 0.05 milliliters or 50 microliters. So using these numbers, I want you to calculate what the molarity of the overall dye solution was. If I used 0.05 milliliters, a drop that was 0.05 milliliters of a 0.01 molar solution, to make a 10 milliliter solution, what was the molarity of that solution in the cup? So just a reminder from last semester, you're using the dilution solution, which is C1 times V1 equals C2 times V2. So you'll calculate what the concentration was in trials 1 and 2 when I used 1 drop of yellow dye, and the concentration in trials 4 and 5 when I used 2 drops of yellow dye. You'll do the same thing for the bleach. The bleach had a larger drop, so I said it was 0.08 milliliters, and it had a different concentration of 0.7 molar, but still a final volume that we're going to go with of 10 milliliters. We're going to assume that those drops didn't significantly affect the volume. Again, this is like terrible chemistry. Chemists are very precise and accurate, and we are kind of estimating these things because we're doing this at home and we don't have the proper equipment to be truly precise. Even I did this at home, even though I probably could have done it in the lab. And so there's definitely going to be some error in our calculations. So this is really more of an exercise to demonstrate rates and rate laws, but do not take this as actual good lab data. All right, also in your lab write-up, I'm going to have you calculate the average rate of the dye disappearance for each trial. So remember, average rate is just the change in concentration over the change in time. And the change in concentration of the dye is really what we're measuring. And we're measuring it by the loss of color. And so essentially we're taking it from the initial concentration down to 0. So we can say that since all of the dye is consumed in the bleaching reaction, that our change in concentration is the total concentration. So that all of the dye is disappearing. So we're going to use that data. We're going to take the concentration of the dye in each of those, and we're going to take the average time that it took for it to become decolored, and we're going to figure out rate by dividing the two, change in concentration over change in time. And then you can fill in this table here of the average rates for each of these trials. Now, we're doing a little bit more fudging in this lab, so what we've calculated here are the average rates. We're going to use these rates to try to calculate the rate law for this equation. In a rate law calculation, you typically use the average rate over a long time period. You're usually using the initial rate in the reaction, but we don't have a way to measure that with our eyes anyway. So when you're doing this last part of the analysis and we're calculating the rate law, the rates that we're using, these rates that we're using, are not exactly correct. They're not really correct, but they work-ish. So, in this reaction, what we have essentially is dye and bleach are our reactants, and they are reacting to form products that have no color, so I'm just calling them bleach dye. So the rate law for this reaction would be K, the rate constant, times the concentration of the dye to the X power times the concentration of the bleach to the Y power. So we need to solve for X and Y using our data. So I want to know first, which trials are you going to use to compare in order to solve for X? And which trials are you going to use to compare to solve for Y? And then in steps 3 and 4, I want you to actually use those trials and solve for X and solve for Y and show me your work. Now, these numbers are not going to come out perfectly. Even in homework problems, they don't always come out perfectly. So you're going to round to the nearest whole number. So whatever ratio you get, it's not going to come out to a solid 1 or 2 or 3 or 4, but you'll round to the nearest whole number so that we can have a whole number so we can solve for X or Y as a whole number. And it will be close enough to round, but it's not going to be terribly close, not as close as it will be in the homework, where like you would round 2.98 to 3. This one's not going to be quite as close to the number that we're looking for. And that's because, again, of all the error in this not very precisely or accurately performed experiment, which is why, chemists use very exact measurements and tools, because the math doesn't work out perfectly if you don't do the chemistry very carefully and perfectly. And so after you solve for X and Y, I'll want you to write out the complete rate law for this reaction, and then also use your data to solve for K, the rate constant, and show your work on that. And that is our kinetics lab.